Hello, everybody, and welcome to another great day of chemistry. So, today we're going to be starting in on the second chapter and the major topic of this semester, which is looking at energy. So, looking at energies, energy changes. Well, as most of these things go, before we really dive in, we have to define our terms. So, big thing is major idea of this semester is we're studying thermodynamics, and that's really just studying how energy moves in within a system and between systems. And so the energy is also going to dictate the behavior of molecules and atoms in a system. If systems have more energy, they're more likely to do something. If they have lower energy, they're more likely to kind of stay put because they're happy where they're at. So, big thing is that if I understand the thermodynamics of the system, turns out I can pretty much predict what the system will do. So the big thing here is if we know what the energy of the system and how the energy moves, we can predict the behavior. And that is the major goal of thermodynamics and honestly physical chemistry in general, is using energy to predict the likelihood of things. So in order to study how energy moves, we first need to define our system that we're studying. So what are we looking at energy moving in and out of? So we have our classic systems that we've seen before. So we have the open system. So previously we defined this as a system where matter could go in and out like an open flask. But a very important idea is if a system can let matter go in and out, it means also it can let energy go in and out. Because this often means not only can I have energy coming exiting in and out as heating, where I can heat a system, but it turns out the matter itself does have thermal energy because it's got kinetic energy. And that thermal energy can exit or enter coming in with the matter itself. So if we constrain our systems a little bit more, we have our good old friend, the closed system. Now, this is where we get a little bit more nuance. So in a closed system, we don't allow matter to come in and out, but we do allow energy to come in and out. So while an open system is kind of like an open flask, a closed system is like a stoppered flask, where I can't have gas coming in or out or liquid even entering in and out, but I can still put it on an oven or put it on a hot plate and heat the system up. That will add energy. I can also shine light onto the system, and that will add radiative energy. So there's still ways for the energy to enter and exit. This brings us to our final system. It is the most boring system and the most beautiful of systems. This is the isolated system. So in an isolated system, matter can't enter or exit, and energy can't enter and exit. So best way to think about this is something that is truly insulated. So imagine if I had your good old Stanley mug, where again, you can leave this system alone for a while and it still won't get any warmer. So energy can't enter or exit. So you'll notice the big thing we're looking at here is how energy can move in or out. And we can do this by describing the boundaries. So if we allow energy to move in or out, like in the open or closed system, the boundaries are said to be diabatic. So diabatic just simply means that energy can enter or exit. This is in contrast to an isolated system where energy can't move across the boundaries. So an isolated system would be said to be adiabatic. So I don't allow any energy to enter or exit. Now, not too surprisingly, one of our favorite systems to start with is going to be an isolated system because in this case, everything is constrained in the system. Once we have good handles on isolated systems, we'll often look at closed systems, where again, I don't have to worry about the movement of matter, but I can really focus on how energy moves. And we'll very rarely deal with open systems because as we talked previously, when matter moves, this gets a little bit more complicated to work with, though still important. So we're talking about energy moving in or out, but what the heck do I mean when talking about energy? So there's several definitions of energy, and we'll go ahead and start with the two ones that are most often used by physical chemists. The first one is the classical definition. So according to classical thermodynamics, so that's the stuff from the 1800s, we define energy as the maximum amount of work that a system can accomplish. So if I have a a container of hot gas, how much energy could I get out of it to do something reasonable, like launch a cannonball or move a piston? So this is the form of energy we're often looking at, is the amount of usable energy I can extract out of the system. Where we just moved our definition because we moved it from energy to what the heck is work. So work is motion against an opposing force. So if I have, say, hot gas, the work it's accomplishing is moving an object. So in a cannonball, the work is moving a cannonball, which is going to want to stay put. So that rest is going to be the force. In a piston, there's usually some sort of resistance where I'm pushing a wheel. So that opposing force turns motion into work. And so we're often looking at how much work can be accomplished. And we can look at this in kind of a classic example. So let's say I've got something nice and beautiful like a waterfall. So the water at the top of that waterfall has lots of energy because that water can do things. It can go places. But if I really want to figure out how much energy it has, one of the things I can do is put a dam across it. Because when I have a dam, in this case, I'm going to extract that energy by making it move against a force. Usually this is going to be some sort of turbine that can actually accomplish work. So again, we can use that change in energy to do work. And again, work is often going to be when we're looking at energy, this is the maximum in the most ideal scenario. How much work could I get out of that falling water as it goes from the reservoir down the sluice? So this is the classical definition. However, as I warned you, there is also the statistical mechanical definition. So in the more modern perspective, energy is going to tell me how likely something is to occur. And it's going to do so by looking at the probabilities. So in the last chapter, I introduced you to the idea of Boltzmann distributions. And this is really what we're looking at here. So the probability of me being in a state is going to be related to the energy of that state, correcting for the Boltzmann constant and the temperature, over pretty much the sum of all of the different states I could be in. And that's what this Q is. It's called a partition function. We'll talk about it at the end of the semester. So the idea here is that if I know the energy of the system, I can figure out how likely something is to occur. Because we have a negative exponential, the lower the energy, the more likely it is to occur. The higher the energy, the less likely. And so if I'm in a high energy state, I'm more likely to move to a low energy state. And by knowing the energy and the temperature, you can figure out how likely something is to occur. Now, this is actually fairly useful, and you've seen it before in general chemistry with our good old friend, the Gibbs free energy, which we will rederive later this semester, where the probability of a reaction occurring, which is really what the equilibrium constant is how likely something is to be a product versus a reactant, is based on the energy of the reaction. If that energy is very positive, it means we have a very small k. It's an unlikely to occur reaction. If that energy is very small, then it turns out we're going to tend to have a large K and the reaction is very likely to occur. Now, a useful thing to keep in mind as we're talking about energy values is that we can use the numerical value of the energy to figure out roughly how likely something is to occur. And something we'll bring up again later is that every change of energy by about 1.25 kcals, or about 6 kilojoules per mole, changes the probability of something occurring by about an order of magnitude. So if the energy is 0, then we have a K of 1. But if it's 1.36, negative 1.36, then our K is 10. So again, it's literally 10 times as likely to occur. And then if it's about 2.8, then it'd be 100, and so on and so forth. So again, very small energy and changes can have big impacts on probabilities. So again, we'll focus less on this Boltzmann distribution, but it's good to have kind of in the back of your mind as we're talking about the more classical thermodynamics. So now that we've got this idea of the importance of energy being how much work I can accomplish or how likely something is to occur, We can also talk about how we characterize it. And we're often going to characterize energy in one of two key ways, either potential energy or kinetic energy. So kinetic energy is probably one you may have seen from physics, and this is going to be the one associated with the movement of matter. And we brought this up a little bit in the first chapter, where the kinetic energy of a system is going to be based on the mass. So heavier objects tend to have more energy. It takes more work to get them moving. And the velocity. Faster something is, the more kinetic energy it has. The larger it is, the more kinetic energy. You can rewrite this in terms of momentum, where momentum is just mv. And so in this case, the kinetic energy is based on the momentum and the mass. But these two are just going to be synonymous. So the big thing is when we're dealing with the movement or kinetic energy of a system, we've got kind of two different ways we're talking about the kinetic energy. Either the system as a whole can have a velocity, or we can have random movement in the system, where bits of it are moving one direction and bits of it are moving the other. So we're not going to spend quite so much on this bulk directional movement because we tend to not launch our flasks across the hall. Instead, what we're going to be focusing more is on this random movement. Because as we saw, in the last chapter, the random movement is just a version of temperature. Because temperature tells you how much random motion you have in a system. The higher the temperature, the more random movement. And so for a molecular gas, this has an energy of 3 half. For an atomic gas, this has an energy of 3 halves kT. For a diatomic, 5 halves, and so on and so forth. So we can use this when we're looking at this kinetic energy, we're mostly looking at thermal energy. And I'll try and be very clear when I'm talking about thermal energy versus a directional kinetic energy. All right, so in contrast to kinetic energy, potential energy is the amount of energy stored in the system that can potentially accomplish something. So the potential energy is going to be determined by how much force is required for you to move from your starting position. So if it takes a lot of force to make you move, it means you have a very negative potential energy. So negative energies mean you're quite recalcitrant. Positive energies, it means it's very easy to make you move. And so for gravitational energy, we can go ahead and express, this is the one you may have seen in general physics. This is based on the height of the system. The higher something is, and the heavier, the more potential energy it is, the more it can do by falling. And in general physics 2, you may have encountered electronic or Coulombic forces, where the idea is the potential energy is stored in the attraction or repulsion of charges, where if these two charges are identical, this gives us a positive or unfavorable energy. But if the charges are opposite, positive and negative, this will give us an attractive potential. And that energy is stored in the distance in between two objects. If two like charges are very close, this will have a big repulsive. If two like charges are or two opposite charges are very close, this will be quite attractive. So when we're looking at this internal and kinetic energy, we can sum these together to get the number that we're going to spend the most time talking about. One of our more common energy metrics, and this is the internal energy. So this is going to be the total of both the kinetic and the potential energy. You can think of this again as the overall or total energy, but there's some important nuances that let us call it the internal energy, as in the energy inside the system I care about. Big thing here is we're going to pretty much ignore any energy based on bulk movement. So we're going to assume the system's more or less at rest. Now, for an ideal gas, there's going to be very little potential energy as the gases aren't going to be too attractive or repulsive. And so the dominant portion for an ideal gas is going to be that kinetic energy, which again, just that reminder that every direction of movement adds 1/2 kT. So for example, if I have a monatomic gas, I have 3 translational motions. This is what gives me the 3/2 kT. For a diatomic gas, I have three translations and 2 rotations. So 5 degrees of movement, which gives me 5 halves kT. And for larger nonlinear gases, I have 3 rotations, which gives me 3 kT. We're going to really ignore the energy from electronics, though that is something that is covered in quantum mechanics. And again, each of these directions of movement is called a degree of freedom. So a diatomic or monatomic gas has 3 degrees of freedom, diatomic has 5, and a larger gas will have 6. So when looking at our internal energy, one of the big things to note is that it is going to be a state function, which means that it's uniquely defined by the state of the system. So if I know the exact parameters defining the beginning of the state, I'll know my internal energy. If I know the exact parameters of the final, I'll know the final internal energy. And the difference gives me the difference. Now, the potential energy will be solely defined by the identity of the gas. So again, how attractive the two systems are. The kinetic energy of the substance will mostly be the potential energy is going to be determined by the identity of the gas, because this will include some parameters such as how stable the gas is. For example, ozone is going to be a lot more reactive than, say, molecular oxygen, and so would be a higher energy. The kinetic energy is going to be defined by several key features. First, we need to know the amount of the substance, more things moving, more kinetic energy. The temperature, because this literally is telling me how fast everything is moving. And again, the big thing here is the identity of the substance, whether again it's monatomic, diatomic, or larger. Now, the big thing here is that we're often going to include the moles and the volume, because this is going to account for my intermolecular interaction. So again, a little bit of that potential. And this is because this gives me the concentration. Turns out the molar volume is going to dictate how the gas interacts, both with itself and with the boundary systems. And so when we combine all of these together, it turns out the internal energy depends on 3 key variables: the moles, the volume, and the temperature. And so we're going to define our state function in terms of these 3 variables. And again, we'll usually put the function on the outside of the parentheses and the variables on the inside. So this is defined by 3. Note, if you're missing one, you can use the pressure to figure out the other 3. But again, that becomes a little bit more tricky. So that brings us to kind of our definitions of energy. The next time, we're going to really dive in to the first law of thermodynamics. Until then, take care.